for the presentation. And thank you for your invitation. As you said, we are going to talk about symmetry and theory and turbulence. And in this project, we are working with many people, but basically this is a project of the PI is Martin Oberlack from the Technische Universität Darmstadt, and myself, and I'm working from the Universitat Politécnica de Valencia in Spain. Well, we have a lot of funding for this project, including 2 projects at SuperMUC. So first, as there are people from many different fields here, let me just give you a short introduction, very short and very brief introduction to fluid mechanics. The point is that fluid mechanics is an open problem, and it has been open for nearly 150 years now. Computationally speaking, there are 2 different things. First one is what we call DNS, direct numerical simulations. For direct numerical simulations, which is what we are doing in this project, we are solving the Navier-Stokes equations, which are very nonlinear, very big, and so on and so on and so on. What is the idea of this? To get science, to get knowledge, in order to be able to transfer this knowledge for the people that do codes for the industry. These are different methods like LES or RANs, which are, for example, the ones that people have been using in the previous talks. Okay, so our idea is not to solve something that we are going to see flying in the next 10 years, 20 years, but to understand fluid mechanics. With this idea, we started with the symmetry theory, okay, in order to do something different from what people have been doing in the last 150 years. So our idea was to understand the high moments of the flow. For that, and in fact, sorry, we are interested basically in the behavior of the flow in 2 different parts of a wall-bounded flows. First, why are we simulating one turbulent channel flow? Here you have one turbulent channel flow. Flow goes from here to here, and you have 2 walls, okay? The top wall and the bottom wall. Why are we simulating this? Because it's the simplest complete geometry of a wall-bounded flow. And these wall-bounded flows are one of the most interesting turbulent flows. We are running it at one number, which is r tau equal to 10 to the 4. What is this? Is one special Reynolds number, is the friction Reynolds number. Okay, this number is very, very important when we are dealing with one flow close to a book. For example, in our case, 1 r tau of 10,004 is a characteristic of a very small area. Okay, really, really small. For a very large jet, we are talking about 10 to the 5 or, well, many 10 to the 5s. We have been running this kind of things for several years in SuperMUC, and we have published one paper about the most dynamic, the fluid mechanics interesting results in the physical review fluids, and another paper about the symmetry theory in physical review levels. Some details, let me tell you some details about this simulation. First, this is our simulation. Excuse me. We are running the simulation for an r tau 10,000 of a Reynolds bulk of 261. This is the size of the simulation, okay? Why are we choosing this quite a strange length for our box with pi? Because we are using Fourier. Okay, this is the size, the cell size in X and Z, and we are seeing here is that our simulation is basically as any other very big simulation ever made. We are running this simulation for approximately 2.5 million steps. We are running this simulation right now, and we expect to run it for 2.8 million. The point is that we are collecting statistics from the flow. And in order to get the statistics from the flow, we have to run it for a very long time. Some characteristics of the simulation. The raster file is 250 gigabytes. Okay, so every image of the flow is 250 50 gigabytes, and we need one mess of 80 billion points in order to run the simulation. The code that we are using is LISO, which is an in-house code. Okay, we started in 2007. The last version is, that was completely made for SuperMUC was made in 2018. And we are using Fortran, MPI, and HDF5 for saving the data. I told you about 200 gigabytes. This takes approximately from 10 to 20 seconds for saving this to this. And we are running typically in 2048 procs. Okay. The code is being optimized in terms of memory in order to use as less processors as possible. The special discretization is Fourier, and a special kind of finite difference in Y, where we have the walls, which is compact finite difference, and Fourier. The temporal discretization is a three-step Runge-Kutta. And about the communication, we have to do for every tiny step 37 all-to-all communications, where we are moving all the data across the machine. For doing this, there were two alternatives. We made MPI send receive routine using one hypercube topology that works a bit better than the MPI all-to-all B that is implemented in SuperMUC. We tested this in one workshop many years ago. This SuperMUC. And for the next version, I heard you asking this to the previous presenter. I think that we have to move to GPU. It makes no sense to use more powerful processors, but we have to move to GPU. So the point is that why are we using symmetry theory? Let me say you first some results from the simulation very briefly. This is the U velocity, the velocity in the stringwise direction. Okay, red points means regions where the flow goes faster than the mean, and blue, the flow goes slower than the mean. This is what happens very, very close to the wall, just 1 millimeter, some millimeters from the wall. As you go up from the wall, you can see that there are different structures that appear, and at the end, we got the Hall fields. We got 80 billion points here. So we need to find some information from here. What people typically do is to find the statistics of the channel and try to interpret that. This is what we have been doing since Raymond. And we have found quite interesting results, okay? This is very specialized, but the point is that our results have been published in a very good journal, and we have found some things that are, let's say, very important for our field. But it's quite difficult, let's say, to show you the importance of these kind of things. Okay, for example, here, this is the stringwise standard deviation of the flow. And here we see that a second maximum is going to appear. This is very important for the modeling community, because in most of the models, they don't think that a second maximum is going to exist. However, we prove that the second maximum is going to exist. Anyway, in order to find a bit more of, let's say, order in turbulence, we started with symmetries. And symmetries is very simple. The point is that you got one differential equation, you do a symmetry transformation, and you got a Fourier variance. When you got this thing through this symmetry transformation, you got a symmetry of the system. Symmetry has been one of the most important theories for physics in the 20th century, but it never was applied to turbulence. Why? Because turbulence is not conserved. Okay. However, we have developed a way of doing it. Basically, because in turbulence is very important, we are always talking about the instantaneous value, which is the value that you see, the mean value, which is the value that you get after averaging the flow, and the fluctuating quantities that we can say that is a kind of, let's say, ordered noise. Since Reynolds, at the beginning of the 19th century, people have been decomposing the instantaneous value as a mean plus a fluctuating quantities. And one of the tools that we have been using for studying turbulence is to use two-point correlation test. People have been focused on this one, the one about the fluctuations, removing the mean. However, we have found that using a new definition based on instantaneous velocity and forgetting about Reynolds decomposition, we can obtain some new equations. And from that equation, we are obtaining new, very important laws. So the problem is that the notation for the multi-point moment equation, where we have infinite points and infinite equations, is extremely, extremely difficult. And as you can see here, we have, well, a lot of symbols, a lot of definition, a lot of everything. The point is that at the end, we are focused on one-point moments of the directions, and that using this theory and a lot of very specialized papers, we get to these laws. This law comes directly from our theory, this one that you got here. And on the other hand, this is Prandtl-von Karman equation that comes from the 1920s. Using our theory, we have the first mathematical proof of this model. And this is quite important because every model uses this law. Using our theory, we have found this value for the streamwise velocity close to the wall, but also for every higher moment. And most important, the value of the first two moments are the most important here because every other one is related to the moment, to the first and second order moment. For example, you can see here that this is the proof that our law, okay, is correct. And this is a value that is very, very important in simulation. This is the Karman constant. Karman constant is a number that has been changing a bit, okay? With this simulation of 10,000, we have got a very good value for von Karman, okay? And moreover, we have been able, as I told you, to prove mathematically this formula for the first. And also, at the center of the channel, let me go here, we have found some new scaling laws that are very important because are one of the few scaling laws in turbulent flows that comes directly from math. In most cases, we don't have enough mathematical tools to prove or to propose one scaling laws. This is the first tool that gives us some scaling laws directly from theory. And the point is that we have tested these scaling laws with our data. And the point is that, as you can see here, the dots are data, the lines are theory, and everything fits perfectly. The same happens with the other two velocities, okay? But with the velocity in the spanwise direction and in the wall normal direction, the theory works. And all the scaling laws that our theory gives fit perfectly to the data, okay? In fact, we have some incredible behavior with the data that we obtain, the exponents that we obtain from the data, and the theoretical exponent. So, as conclusions, we have a new set of DNS that we have run at the highest Reynolds number ever. Okay, we have found a very nice logarithmic behavior. in one very long interval, and we have proved that this is what happens. That what happens mathematically. Okay, and the data confirms all the equations obtained through symmetry theory. What are we doing now? We are expanding the simulation, and we are trying to get some new scaling laws. And I think that I am almost out of time. So if you have any question,